Hey, all right, hello students. We're about to start now lab number 4. And so this is our 4th video lab. And maybe things are starting to come together here, maybe not. And so maybe we should talk about, turning them into Canvas. But it seems like you guys are getting better at understanding Canvas and how to get on the virtual desktop. And so maybe more on that as we move forward here. But I'm going to just hold this up. This is what I sent to you. This is the instructions on Newton's second law. And that's the title of today's lab, Newton's second law. And so we're going to study Newton's second law. And the way we're going to do this video lab, like I mentioned on the other ones, is I'll do the part that needs the hands-on stuff, the stuff here in the lab. I'll get the equipment, I'll set it up, I'll run the equipment, but I'm going to let you then do the calculations. And actually, your job might require more than my job this time. And so instead of me running around, you've got a lot of calculations to do. So let me hold up this page too. So this is the second page I'm sending you, and this is going to be the first page you turn in. You're going to turn in a total of 3 pages today, and this is one of them. And maybe I'll just point out why I'm here. It's a little early, but we're going to make a graph of this data and a graph of that data. So you're going to have 2 graphs. So you're going to have this data table and two graphs. Okay? And I'm going to call it 3 parts because we're going to do table 1, table 2, and table 3. And each of them will be involving Newton's second law. And really that's the point, because learning Newton's second law is a little challenging. And so we are learning that, actually all of Newton's 3 laws is a little challenging, and that's why we're learning them. And so in lecture right now, we're doing chapters 4, 5, and 6, each involving Newton's laws of motion. And of course, then today, we're doing a lab on Newton's motion. In fact, tomorrow will be one too. So we are trying to figure out this whole concept of dynamics, of explaining the motion here. Now, let me get started by kind of showing you the equipment, all right? And so I set up a Pulley system before we started the video camera to save a little bit of time on video. And you can see that I've got 2 weights that are connected together. And right now, this one, which I'll call M1, is the lighter of the 2. And so if I pull this down, and then, let me put my marker down, let it go, you'll see, and I'll just kind of put my hand under there in case it falls off, you'll see that the heavy one pulls down the lighter one. And we're going to use Newton's laws of motion to kind of analyze this. All right, let me go over to the blackboard, or excuse me, the whiteboard here and start talking about this. Now let me draw a picture first. So if you noticed, there were 2 pulleys and then a string that came to the heavier one. Let me call it M2. And then over here, down on the top of the table, was the lighter mass, M1. And of course, to hold all this up, I had a little bench rod that was connected to my laboratory bench, and I had a right angle clamp right here that would clamp the post of the pulley here. And that's what you were watching. Now, here's how I want you to think about it, and that is, think about this as one object being tugged to the right by the weight of this one, and to the left by this one. Here's how I like to draw it. I like to say, imagine taking these weights and straightening them out I would say that this one is being pulled to the right by a force of m2g. And that's how we calculate the weight, mass times g. Now, I know technically it's being pulled down, but again, hopefully in your mind, you can see this as a one-dimensional tug of war. I only put it around the pulley so that I can control very accurately the two forces. And so again, I'm going to be your hands, and I'm going to put different weights on here. And when I put different weights on here, that's going to then determine which one is stronger in the tug of war, and by how much is it stronger. Okay, so on the other side, I would call this M1G. Now let me take a different colored marker for a second and keep emphasizing what I'm trying to say in class. Make sure you kind of understand in the discussion what the object is. And for this one, it is not just an individual mass that's my object. My object in my mind is the two of them together. You might even say this then, that the total mass is M1 plus M2. All right. So what I want to convey to you is to think of this as a single object that has a mass that's the total, and that it is in a tug of war between two forces. One of them is pulling it to the right, and of course it is equal to the weight of object number 2. The other one is pulling it to the left, and of course it is equal to the weight of number 1. So that's the battle going on here. Now let's not forget that there would be a little bit of friction in the pulleys. And part 1 is to demonstrate how little this friction is and to justify why we're going to kind of ignore the friction when we get to step 2 and step 3. Okay? But part 1 is really nice because not only does it show that the friction is small, it shows how we would handle it. All right? So, excuse me. So let's try Newton's second law. And let's try it both with and without friction. So if I were to do this problem without friction, versus with friction, what would be the difference? Okay, let's do it without friction. So for a moment, let's imagine there is no friction. And so when somebody says calculate the net force and set it equal to ma, excuse me, maybe I'll take a quick sip here. Got my water close. Okay. I would do this. I would say M2G minus M1G and stop right there. That's the net force because the net force is adding up all the forces, and if I'm ignoring the friction, there's only those two. And that has to be equal to the total mass. So remember, I'm thinking of that as one object, so I'll put M1 plus M2 times the acceleration. So let's call this the calculated acceleration. But I would also say it is probably higher than reality because, excuse me, because reality is going to have a little bit of friction in there. So that's why the first step is to calculate what the acceleration would be for a problem like this without friction. And then the second step is actually measure the acceleration to see what it comes out to be. And hopefully, what we actually measure is kind of close, but just a little bit less. All right? Now, let me come back over here because I have shown you on this data sheet, and maybe I should stand out of the brightness of that display, but this is going to be your step, okay? So I won't do this. This is going to be your job. Your job, and it would be good to maybe do it right now and just kind of pause, and you don't have to hit stop, Ron, because I'm just going to keep going. Oh, you're zooming in, okay. But right here where it says calculate the acceleration, what they're asking you to do is what I just said right here. Calculate what the acceleration would be in a perfect frictionless world, okay? And that is why you have your calculator. And so if you look closely at this data table, you will see that they list M1 and M2, and they begin to change M2 each time. So there are 7 different values of M1 and M2. Now, M1 always stays the same. It's 200. Now, let me give you a warning. It's 200 grams. So keep in mind that when you go to do your calculation, change this to kilograms. So that would be 0.2 kilograms. So I'm going to say it again. If you take this first column, in fact, you know what? I'll help you set up the first one. That might be good. The first calculation would look like this. Looking at my chart, M2 would be 0.22 because it says 220 grams, which translates into 0.22 kilograms. G is 9.8. M1 would be 0.2 kilograms, because again, the chart says 200 grams, times 9.8. If I add them together, so 0.2 and 0.22 become 0.42 kilograms. Then you can see the only thing I don't know is the acceleration. And so, like I said, your job, and I'm just going to keep going, so if you want to, pause, go through these 7 calculations and find out what the acceleration should be in a perfect world. That is, if I hook these up and there was no friction, this is the acceleration I would get. Because what I need to do for you is the next column. The next column says acceleration measured. And so you can see it a little clearer. I'm going to put it on the board here. First one, second one, third one, fourth one, fifth one, sixth one, and seventh one. And so let me actually hook up the weights as they describe, and hopefully as I go along here, the accelerations I actually get are going to be a hair lower than what you calculated. Because I'm going to say it again, what you calculated would be the acceleration without any friction. But of course, when I hook it up, there's actually going to be some friction. However, these pulleys have pretty good bearings in them. And so even though there is some friction, it's a pretty low value. And that's what I want to convince you of, that not only are you learning about friction, but then in part 2 and part 3, you'll see the justification of why we'll just say, don't worry about the friction. It's so small compared to all the other forces, it's what we call negligible amounts. And so, you know, if you have $10 and somebody hands you a penny, you're like, yeah, thanks. Or somebody takes a penny for you. Oh yeah, big deal. You know, it's just negligible. You still roughly have $10. You know, it's just a penny up or a penny down. It's just insignificant. And so that's what we're going to see here with the friction here. All right. So let's talk about how we're going to measure it. Now, let me show you the equipment again. And it looks like my string fell off my pulley, so let me put it back in here. And I will point out, like we did in the acceleration one, I have that little photo gate right here. And that photo gate then is going to have a little infrared beam that when the pulley turns, the spokes in the pulley will chop that beam. And so this is our second time using what we call the Logger Pro equipment. And the Logger Pro equipment is designed to do a lot of crazy things. And you've already seen this one, so there's not really new other than I'm not dropping a picket fence. I'm spinning a wheel that has spokes. But it'll be able to measure it. All right? So why don't I start collecting and then helping you with the measured acceleration. All right. So if I grab my little worksheet here, it says on the lighter one put 200. Okay, so I already set that up. So here's 200. And that won't change at least for this table. Okay, now on the other side put 220. And I think I'm a little high on that because I was trying different values. So let me just check out. Yeah, so here is a 100 for the mass hanger, thank you. 100 that's on here and another 20. And so this is a total of 220 grams. So now we're ready to do the first one. And like I said, if I let this go, there it is. It has an acceleration. And I'm going to use the photo gate here. Oh, I see. I'm tilted back a little bit. Let me make a quick adjustment here. Before I kill myself here. Okay. The pole was tilting backwards, and because of that, the weights were coming off the table. They were right on the edge. All right, let me try it again. Oh, my microphone kind of fell down. Check my sound there, Ryan. Ron?
It's still on.
Still on? Good. All right. So it'll look something like this. Do, 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 do. Okay? And it'll hit right there. Now, what the computer is going to do is record that distance. All right, so I'm gonna begin. And so I'll get ready. So here's our first one. And we're gonna do 17 of these. And so I'll start off and turn the screen a little towards me. And I'm going to hit collect, pause, I'll let it go. Now it crashes, and after it crashes, I'll hit stop. And sure enough, you'll see that the computer has given me the distance, and maybe I should say that each spoke is 0.015 meters. So this would be the first spoke, the second spoke, the third spoke, and so forth and so on. But do you see how it gave me that parabola? Do you remember when we did the picket fence, how we got the acceleration due to gravity? We actually got it a couple ways, but one of the ways was to plot distance versus time to recognize it was a parabola, and from that we can get the acceleration. And that's what I want to do here with you now. So I'm going to remind you of this graph. When we plotted distance versus time, and we had this parabola, and we curve fit it, we got something that said capital A t squared plus capital B t plus c. And that was our curve fit. And when we compared that to our kinematics equation, we could see how the initial position lined up with the constants. The initial velocity lines up with B, and we don't care about those. The one we cared about, and the one we'll care about today, is to see how this capital A here matches what's in front of the t squared, which is 1/2 the acceleration. So 1/2 the acceleration. And then when we move the 2 to the other side, 2 times capital A is the acceleration. So that's what I'm going to do here with you right now. What I'm going to do is do a curve fit. And I'm going to find that value of capital A. And when I find capital A, then I'm going to double it, and that's going to be my measured acceleration. All right, so using the computer and recognizing that this stuff up here, which looks kind of funny, must have been the part after it hit the table. Okay? So I'll curve fit from about right here on back and do a quadratic curve fit. All right, so I will do Analyze, I will do Curve Fits, I will select Quadratic, and I will go try Fit. And I will recognize, yes, it matches really well. So then I will click OK. And now if you look at the screen, and by the way, I'm not going to print this. We're going to make 14 of these, but I'm going to save a tree and not print them. I'm just going to say I'm going to use this to find the acceleration. So the capital A is 0.21. They give 4 digits, but let me just use 2. So I'm going to call it 0.21. So if I then double that, it becomes 0.42. And so I would say that I have just now, with you, measured, and so like I said, we're a team player here. I have measured 0.42.
Units?
Oh, and then yes, meters per second squared. Thank you. Now, I'm going to come back over to here and remind you that you should have done this calculation already before I did the experiment, and I'm hoping you got an acceleration that was a little bit bigger than that. If memory serves me right, you should get a calculation that's about 0.46. And so what we calculated was what the acceleration would have been without friction. What we actually measured is what is it with friction. All right, well, again, this is where I have to do my part of the lab. Let's go through these 7 and measure each of the accelerations. All right, so I'm going to do it again. This time I'm going to add 10 grams. So now I have 230 on the heavy one, And I'm not going to touch this one. This one always says leave at 200 grams. And let's run it again. All right, so I'm going to put the lighter one down on the ground, heavy one in the air, hit collect data, wait and let it go, let it crash. Once it crashes, hit stop, and I'm going to do a new curve fit. Now, I do need to be a little bit careful. Let's look at this curve fit. I still have the curve fit from the old one. I'm just going to adjust it a little bit. You see this little black marker? It goes to where it crashed. And that kind of makes sense because with this heavier weight, it should have gone faster. And so I can see it crashed a little bit sooner than it did last time. It didn't take as much time. So I don't want my curve fit to be part of the crash, so I'm going to move that end of my curve fit in a little bit. And now I got my second curve fit. And I'll help you out here. Notice it says 0.31, and I'll just do 2. So if I double it, that's 0.62. So 0.62 meters per second squared. Now again, I didn't do this, so I hope you did it. When you calculated your acceleration, I hope you got something just a little bit bigger than this. Because this is the real acceleration. This is the acceleration you get with friction, but a small amount of friction. All right, let's try the third one. The third one says add another 10 grams. All right, so let me just check. This is a 10 grams, and so is this one, so I'll do this one. So now I have 240 on here. And let me try the third one. So I will hit collect, pause till it's ready. Okay, now it's ready. I'll let it go. It'll crash. I'll hit stop. And actually, sometimes it stops on its own, which that time it did. Sometimes when it shakes so much, it shuts off. Maybe I will do an auto fit. I don't think I got the anything past the crash. So see how it curved it, and I didn't see anything after the crash. But that's fine. I don't need to see anything after the crash. I just need enough data before the crash so I can get the acceleration. And since we're going to be going faster and faster, it might do this for the rest of this table. They'll slow down on the other table. But so let's see what the acceleration is here. So it says 0.41, so if I double that, that's 8.2. Now, I'll make that same comment. This is the real acceleration. Hopefully, what you calculated was something a little bit higher because that did not include friction. Okay, well, let me go one more. Let me go to what am I at? 250. Okay. And so, oops, I forgot to put it on there. Let me loosen this up. I begin to panic because somebody just came in and took my weights and I'm going to need some of them. So I'm going to go grab them in a second here. Just a few. But let's do the 250. 1, 2, 3. And then I'll just need 3 more 10s. All right, so let me lower this down. Let me get ready and hit collect. Ready and go. And it will crash. And this time it didn't stop on its own. That's fine. But again, looking at this data, and there is where the end of the curve fit is. So again, they're going faster, so it's less and less time. Let me grab the end of the curve fit and move it in to before the crash. All right, And then see what number I have. So that is 0.51. Let me double that. And so that would be 102. 1.02 meters per second squared. So sure enough, it keeps increasing, and hopefully sure enough, it is always just a little bit lower than what you calculated. Now, like I said, I need to grab a few extra weights. I'm going to be right here. Give me just a second. I'm going to grab.
Sorry about that.
No worries. No worries.
I had one down there. I'm sorry, you stole it from me. Sorry about that.
No.
You want to take the whole tray back?
Oh, I could, huh?
I didn't. I'll just bring this one back to you. I didn't see it down there. I thought there was only one tray. There we go.
That's cool. All right. Thank you.
Got that? Yep, you got it.
All right. There we go. All right. Got a big old tray here of weights. All right. All right. Let me just put a few right there. And let's keep going. All right. So, let's see, what was I on at? 250. So let me go to the next one. And here's a 10 gram. I'll put that on. So let's try the 260. And I need to put the string back on. Okay, good. Now it's going to go really fast now. But I'll hit collect, give it a pause, let it go, there it goes, and oh, grab that one, and I will hit stop. Okay. Now this one here, let me do a quick curve fit. I'll bring this down right about there. Okay, so that is 0.60, and then I will double it. So this will be about a 1.20 meters per second squared. Okay. All right, so let me go again to 270. Let me just double check, that's a 10. Okay, there's a 10. And so that should be a 70. Let's see, 20, 30, 40, 50, 60, 70. Yep. And so again, this is going to keep falling off every time. But it's going super fast here. Okay. Ready, collect and release and catch and stop. Okay, nice. And so again, let me just adjust the curve fit. And so I'll say it again, this is kind of my job here, is to be your hands during this. And it looks like now I have 6'9". So 6'9", and I double it. Is that a 1.38 meters per second squared? All right, and then finally the last one here, and maybe the hardest one of all. The one that goes really fast. As long as I don't break anything, I'll be happy. And so number 7 here of our first data table. I'll hit collect, 1, 2, 3, and release, and catch, and stop, and then adjust the curve fit, and take a look, and it looks like I'm at 77, And so if I double 77, let's see, 7 is 14, so that'll be a 15. There we go, with a 4. Okay, so 1.54 meters per second squared. All right, now that's really my work. But let's talk again, because you have some work to do again now. Look at the third column here. So we actually then could figure out how much friction there is based on this real acceleration. I'll say it again, your first column that you calculated, this was the acceleration without friction. But what I actually measured was the acceleration with friction. So if we use the acceleration that I actually measured, or I should say we measured together, you should be able to calculate this third column. And that's going to be your job. Now, I'll help you get started, but I'm not going to run through it. This is where I'm going to leave it to you to do some of the lab. You already, like I said, calculated the first column on your own, and now you're going to calculate the third column on your own. But I'm going to help you get started. Let's come over to here. If you remember, I started setting this up and started to ask you, how would you calculate Newton's second law if you included friction? Because earlier we did this without friction. And I would say it would almost look like this, except it would have one more force, the friction. So it would look like this. It would say M2G minus M1G minus friction equals. Let me pause right there. See, that's the difference. Newton's second law always says you must add up all the forces. So when we were ignoring the friction, there was only two forces, the weight of the individual masses. But now that we're including friction, there are three forces to add together. And it's a net force, so we have to watch our direction. So M2G is to the right, but the other two are to the left, so they get negatives, and that's the new piece that did not show up here, because here we just assumed there was no friction. Now, of course, it would equal to the total mass again, M12, and I hope I gave myself enough room. And then this would be the acceleration that I just measured. See, this would be the acceleration right here. And here's what I claim. Don't we know everything in this equation except for the force of friction? I'll help you get started. But if I move this to the other side for the force of friction, and then I maybe take this and factor out a G, and then take this and move it to the other side, we, or I might say you, should be able to figure out how much friction there is. So use the masses, use the acceleration that I helped you measure, and get out that calculator and calculate the friction in the pulley each of these 7 times. And also make sure you look closely at that number of friction, because you will find it's pretty small. And so, like I said, the whole point here of part 1 is to give you a little exercise about friction, Newton's second law, but it's also to convince you that the amount of friction in these pulleys is pretty small. So now when I go on to part 2, you'll see why I'm just going to not even worry about the friction. I'm just going to overlook it.
Friction is units.
Okay? And, oh, and as Ron is pointing out, make sure when you put down your answer, there's units for friction. And I'll just say, it's the units for every force, which is newtons. So friction is measured in newtons, weight is measured in newtons, tension is measured in newtons, normal force is measured in newtons. Okay? And so when you go through here, you'll have this in kilograms and this in meters per second squared. And so when you multiply them together, that is a newton. And that's what we talked about in the lecture for chapter 4, the units for a force. And so make sure you put that in the table, that you're putting down a number and then a unit. Okay, so I would say we're done with part 1. Let's talk about part 2. Now, I will go ahead then, if you'll let me here, and clean up this board. And I guess you could rewind the video if we needed to come back to it. But I don't think we need to talk about the physical layout anymore. And maybe just for reference, I'll leave the one-dimensional picture of what's going on and how there's a little tug of war here. Maybe I'll also leave this on here because we're still going to measure some accelerations here. But here's what we're asked to do in part 2. Part 2, and so maybe I'll just put right here, is essentially try to take some data that says if you change the net force, what would be the acceleration? And this is measured acceleration. So what I actually measure is going to be, I'll say it again, a hair smaller than what you would have done if you've calculated it, because there is a hair amount of friction. But I want to convince you that if I measure the acceleration, it will come out very, very close to it being calculated, and hence this will be a verification that Newton's second law actually works. Okay? So, what are you going to do? Well, you'll see that in part 2, they give you mass 1 and mass 2. Now there's only 5 of them this time. Let me only put the first one down here. But I do need to measure for you all 5, 1, 2, 3, 4, and 5, all 5 accelerations. What I'm going to ask is for you to calculate the net force, ignoring friction. Now, I guess I erased it up here, and maybe to help you out, I'll put it again. If we ignore friction, so I'll cross that out, there's only 2 forces. The M2G is to the right, and the M1G is to the left. And so I'm going to ask you to pause this video in a second and take your masses. Here's number 1, here's number 2. Put them into this calculation and then fill out these 5 net forces. Because then what we want to test together in this lab is if we then measure these 5, will they come out in a pattern that looks like this. Because this is how you would get the acceleration if you calculated it. And I want to emphasize, I'm not going to calculate it. I'm going to measure it. And then I'm going to see, are my measured values following this mathematical pattern? And if the answer is yes, then hopefully I'll say, hey, Newton's second law is right. And if they don't match, I can say, Newton's second law is wrong. Or I did something wrong. Probably more like I did something wrong than Newton's second law is wrong. But hopefully I will do it right, and hopefully you will see that our measured accelerations do match the calculated values. And we won't even calculate the values, we'll just make a graph here. All right, but before I can do that, let's actually then fill this in. So you guys hit pause, calculate these. When you're done calculating, unpause it, and now let's do this. All right, so let me hook up the equipment here. It looks like it went to sleep, and it's going to be the same kind of experiment. I just need to know what masses I need, and it looks like I need 240 on the lighter one. And so I already had 200. Let me put 40 on each, or 220, so 40. So that one's 240. Now this heavier one, I believe, was 270. But I'm just going to take off all of those 10s and grab a 50. So this is 250 and then a 10. So the heavy one is 260. The lighter one is 240. Then we'll just change the weights as described here. And let's measure the acceleration. So let's do it 5 more times. I told you we're doing this total of 17 times. So we've already done 7. And so we got 5 in this table and 5 in the next table. Okay, so here we go. Let's find the acceleration together. All right, so I'll hit collect and let it go and just catch it and hit stop. And this one went a lot slower than that last fast one, so I'll increase my curve fit out here and say, all right, what is the acceleration? It looks like I've got about a 0.17, and then let me double that. It's a 714. Now I'll just do 2s. So 17 doubled is 34. So this would be 0.340 and meters per second squared. All right, like I said, I'm your hands here. You're the brains, and I'm the hands. Does that make me the bronze, I guess? All right, so you're the brains, I'm the bronze. All right, let's see what it says next. Now the next one says let's lower this by 10. So I guess if I took a 20 off but replaced it with a 10, that would now be at 230. And if I put that 10 then onto here, this would go up to 270. And by the way, then did you notice that the total mass didn't change? I took out 10 off of this one and put it onto here. That's important because we're trying to see how having more of a net force, so more weight over here and less over here, will change the acceleration, but without changing the mass. And so if you look at this whole table, the masses always total up to be 500. And so that's an important part of this. We want to see how the acceleration is going to change with net force, not with mass. That's coming up in part 3. So we want to make sure we don't change the mass. We just want to change one factor, and that's the net force. All right, so let's do the second one here. All right, so here we go. I'll put this down here. I'll hit the collect. I'll pause and let it go. Catch it and hit stop. And I don't even see the other end of my curve fit, so I can't really grab it. So I will just have to redo it completely. Quadratic, oh good. Try fit, okay, good. Hit, okay. All right, same logic. Let's get the acceleration from this. So here's a capital A. Let me just call it 0.45. I double that, and that's 0.90. Wait. Did it change by that much? I'm a little bothered. Maybe that's good. Let me just check. Did I mess up on my weights? 100, 200, 230. Good. Oh, I did. Okay, let's try that one again. I'm glad I checked. That was a big change. Remember I said I was going to put the 10 on there, and I actually put the 20 on there because I took a 20 off and put a 10 back in its place, and I put that one on there. That was my bad. All right, I'm going to try it again. All right, so 200, 250, 60, 70. Yeah, okay. All right, yeah, no wonder that one went so fast. Okay, so let me erase it. Oh, I never wrote it down. Okay, good. Let's give this one a try. So let's redo number 2 here. Okay, ready, collect and go and up and catch and stop. Nice. All right, so now let me go ahead and adjust my curve fit a little bit. Good. Let's see what I have. So I have a 36. Doubling that is a 72. Wait, what? Okay, guys.
Go try the first one again?
Yeah, maybe I did the first. Let me double check. But maybe this is good to have a little bit of confusion here. So that is 230. This is 50, 60, 70. 270.
Yeah, that's good. Oh, yeah.
Okay. So 72. Maybe I should. Wait. Wait, is this so bad? Didn't I had a difference of 20, now I went to 40. So I doubled the net force and I roughly doubled the acceleration. Okay. No, I don't think there's anything wrong there. Yeah, okay. I was just panicking. All right. So, all right, let me keep going and see if there's any other reason to panic. All right, so let's give this a try. All right, so let me take a 10 off of here and double check that that's a 10. Okay, so this is 220. And let me put it onto this one and double check. So this should be 280. So 250, 60, 70, 80. Okay? And then let's see what kind of acceleration we get together. All right, so here's the third one for part 2. So I'm going to hit collect and go and let it go up. Oh, and catch it and hit stop. And okay. And I hope I got the right bit of curve fit. Maybe I'll check this one too, because it looks like it bounced around a little bit and did something that's making me a little nervous here. But 55 twice is 110. So let's see, if I call that a 35, if I double it, that would be 70. If I triple it, that would be 105. So yeah, we're on pattern. And then of course the units are meters per second squared. All right, well, these other two, they really go fast. So I'm gonna be a little careful here, but let's get the acceleration going here. This one says lower it down to 210. And so I'm gonna have to take off a 20 and replace it with a 10. So that's 210. And over here then needs to be 290. And maybe I'll just grab another 10, put it on. And double check. 200, 250, 60, 70, 80, 90. All right. And yeah, I can really feel how heavier this one is compared to the other. So this is really going to be speeding up. Okay. And so here we go. I'll hit collect and let it go and definitely catch this one. Then I'll come over here and hit stop. And then I'll move my adjustments of my curve fit. And it looks like I'm at about a 0.74.
I'll get you off.
I think I'm far enough over. I think so. It follows pretty good here. So let me call it a 0.74, because if I double a 7, what do I get? A 14. If I double a 4, I get an 8. And so this would be 1.48 meters per second. 5. Yeah, which again is about a 35 increase. So it's roughly following the pattern. Okay, good. And it looks like this one bounced so much that the tension twisted this a little bit. In fact, I'll worry about straightening it after I adjust the weights. All right, so finally the last one for part 2 is to lower the lighter one down to 200 and the heavier one more 10 for a total of 300. So quite a significant difference in these two weights, and hence quite a significant net force, and hence quite a large acceleration. And I'm pretty sure this is the biggest one of the day. I think the other ones go slower, if I remember right. Now they must, because we keep putting more mass on them. Okay, so let me get this last one for part 2 going. And say, all right, ready, collect, and go, and catch, and stop. Nice. And then I'll adjust the curve fit so that it's before the crash. And it looks like we get a 0.93. So if I double a 9, I get 18. Double a 3, I get a 6. So 1.86 meters per second squared are the 5 accelerations that is why we're working here together. All right. Now, what I'm going to have you do, but I'll wait until after I collect the other data, is to say, plot this with graphical analysis and see if it follows this pattern. But before I do that, let's go ahead and you do a calculation and I'll do some measurements here, and let's collect some data where instead of changing the net force, we'll change the mass. And so in the table here, you will see that in number 3, we always have a difference of 20 grams. And so we don't change the net force, but we change the mass. So let's collect our data and have you do your calculations. We'll see what happens. Your table will look something like this. You'll have mass 1 and mass 2, and then you have a column that says what is the total mass. This is the part that you need to calculate. And so for the first column, go ahead and add the 150 and the 170 to come up with 320, and this is all, of course, in grams. And you should do the second calculation, the third calculation, the fourth calculation, and the fifth. So that's what I'm going to leave to you, because again, we will do a measured acceleration, and then hopefully we will ask, does what we measure match a pattern of Newton's second law? And so let me come back over here to part 2. I haven't actually plotted it yet, but I'm hoping when I do plot it, it'll match this pattern. Let's talk about that pattern next. But I'm also hoping that when I plot number 3, or I should say you plot number 3, or part 3, that it'll follow this pattern. And so we got to talk about that pattern, because in part 2, you're changing the force but not the mass to see how it affects the acceleration. But in part 3, you're changing the mass but not the force in order to see how it affects the acceleration. And so if I can use some fancy math terms, in part 2, since it's in the numerator, we should see a pattern that is proportional. But in part 3, since the mass is in the denominator, we should see a pattern that is inversely proportional. And so hopefully you'll see that, because again, the idea of plotting this data and collecting this data is to convince you that Newton's law actually works. And that's why we're measuring the accelerations, not calculating them. All right, so we got quite a bit of work here to do to get 5 more, our last 5 accelerations here. Okay, so let me bring my mass here close, because I'm going to now change the lighter one to 150, and the heavier one to 170. So the hanger's already 50. I'm sorry, 100. And I'm going to put a 50 on there. And also a 20. Let me find a 20. Here's a 20. So this is 170. And by the way, then the lighter one over here, I just put a 50 on the hanger. Remember, the hanger's 100 and the lighter one is 50. All right, so following the lab sheet's instructions, I have a lighter one at 150 and a heavier one at 170 grams, okay? And so let's get their acceleration. So I'm gonna hold down the lighter one, I'm going to hit collect. I think this doesn't go too fast. Collect, let it go up, maybe catch it and hit stop. And then adjust my curve fit. Whoops, I missed it. Adjust my curve fit. Right before the crash. And it looks like 0.29. So 0.29, if it was a 30 and I double, it would be 60, so it would be 2 less than that, so it must be a 58. So right here is a 0.58 meters per second squared is the acceleration. Now, if you look there, we're going to add 100 grams to each of them, and we're going to keep doing that. So I'm going to come over here and just grab a bunch of 100s. And I think I need probably a total of 10 of them because I'm going to just keep adding. Well, I think I only added 4 times. So I need 8 of them, and I got more than that. All right. So this 150 will now be 250. And this 170, by putting 100, will now be 270. And so notice the difference is still 20, but the total mass is quite a bit more. And the math would say, since the mass is in the denominator, we would call that inversely proportional. This should have less of an acceleration. So let's see what we have. I'll hit collect, pause, and let it go, and then put my hand underneath it and hit stop. Oh, good, the shaking stopped it for me. Maybe I will even then adjust the curve fits, although we actually have quite a bit. But let me call that a 0.16. Because when I double 16, I get 32 meters per second squared. So, sure enough, it went down. And without a calculator, I can't really check if that's right. I'm going to trust it's right and go to the third one. The third one again says, put 100 on each side. So my 270 is now going to become 370. And my lighter one, which is 250, will now become 350. And so, let's try this acceleration. So I will hit collect and pause and then let it go. Much slower. I don't even know if I need to catch it anymore. But there's my curve fits. And again, it's taking a little bit longer. So I'll move my edge of my curve fit out. But it looks like my capital A is about 0.11. So I will double that and go 0.22. And so again, a lower acceleration. Second to last one. I will put another 100 on here, making this 400. 1, 2, 3, 4, and 70. And putting 100 on here, making this 450. And so we're getting a lot of mass now. Should go real slow. I'll hit collect, let it reset, let it go. Maybe I'll just put my hand underneath it and hit stop. And maybe even adjust the curve fit a little bit. And it looks like now I'm at 0.08, but maybe I'll go 8.3. and double that. So 16.6. 16.6 meters per second squared. So real slow, real sluggish. And finally, our last one here together, and then we'll talk about the labs and then we'll be done, is to say, let's put one more on here. And so what am I at now? 1, 2, 3, 4, 570. Is that what it says? Yeah. And I'll put 100 on here. And I will get it ready. And I will hit collect. Let it go. Hit stop. And I won't even adjust the curve fit. I'll just use that number. And so that's 0.069. Let's see, double a 6, that's a 12, 13. So 138. And so the acceleration is 0.138 meters per second squared. And that's the acceleration. All right. So, like I said, I'm your hands in the lab. And what you need for an online lab is somebody to hook up those weights and run the computer so we can get these numbers. You did a bunch of calculations, and now you're going to make 2 more graphs. Okay? So I would encourage you to shut down, well, I was going to say shut down Logger Pro. You don't need to do that. You're never going to turn on Logger Pro. I'm going to shut down Logger Pro. Okay? So here I'm going to shut down Logger Pro and go to Graphical Analysis. And that's what I'm going to ask you. Go to Graphical Analysis and right here make 2 columns. And here they are, right here. Change the X column into net force and type in these 5 values that you calculated earlier on. And then change the y-axis into acceleration and type in these values that we measured together. And your graph then should look a little bit like this. You should have acceleration on the vertical axis and net force on the horizontal axis. And if your data kind of looks like a nice straight line, that is the proof that it's proportional, right? A straight line is proportional. Newton's second law, this map says that these 2 factors, if you don't change this one, and that's what we did here in part 2, we changed the net force to see how it affected the acceleration without changing the mass, and the math here says they should be proportional, so we actually measured some real acceleration, and we are hopefully seeing it is proportional. And so your second page to turn in, and I say that because I'll repeat, this is the first page, okay? This all filled out. So this is the first page to turn in. But your second page then is this graph. A graph of the data we got together in part 2 that shows it is proportional, that proves what I would say half of Newton's second law, because the other half is to prove that it's inversely proportional to the mass. That's what we're going to do next. But you're proving these 2 are related as described by this equation because of this graph. Now, I'm going to ask you to do a second graph, and your third and last piece to turn in for this lab is to make a plot. Again, you have acceleration on the vertical axis, but mass and total mass on the horizontal axis. And so I would say once you have typed in your data for part 2, just type over it for part 3. You'll have to change the X column to be mass. But the second column could still be titled acceleration. Now, this graph should look like this. Because an inverse proportion plot, and maybe I'll just kind of remind you from your algebra class, if you have something that says y equals something over x, I'll just make up a number like 10 over x, it has this dropping down hyperbola shape. And Newton's second law is saying that. It is saying it's inversely proportional to the mass. So we want to know, did the data we collect match a pattern that is inversely proportional? And so you are to curve fit it to an inversely proportion. And that's the last thing I want to show you, because I showed you how to curve fit to a proportional or a linear one, but I haven't shown you further down on that menu that there's also an inversely proportion. So, as I wrap up the video lab here, let me point out that if you go to Analyze and you go to Curve Fit, and I'll just pause right here, you can choose proportional or linear here for part 2. That I didn't show you because I thought you knew. But notice there's a scroll bar over here. So I'm going to scroll down a little bit more. And at some point, oh, there it is. There's an inverse relationship. A constant over x. Inverse relationship. So click on the try fit. And it should match pretty good. Now remember, not perfect because there really is friction. Okay, and so all of this is saying we've done this without friction. But there really is friction. So your data and your curve fit won't be an exact match, but it will be kind of close. Quite close. Okay? And so that's your last step. So I'll say it one more time. You should be turning in 3 sheets of paper. The first sheet should be this data one that we went through. You did a bunch of calculations. I measured 17 different accelerations. Then, using the data from part 2, you should have made a plot of acceleration versus force, and you should curve fit it to a linear, so that'll be your second page. And your third page should be from your data on step 3, or part 3, where you plot acceleration versus mass, trying to show that it has an inverse relationship, so it does curve fit to an inverse relationship. And now, I would say you've just done a verification that Newton's second law is valid, and so all these homework problems, all we've been doing, when we calculate what the acceleration is, we can trust Newton's second law. We can actually build a rocket now and figure out what the acceleration should be. And we can trust it. And maybe we could actually get to the moon. Or maybe the next step is to get to Mars. All right, but I'll call it quits for now and say goodbye, and I'll see you in lab number 5 coming up.